All right, so today I want to talk about the ultimate 3D toolpath. I have some notes written in front of me just to try and help me keep on point or on message here. We'll get into some of the CAM stuff first, but I want to talk about this concept and why I'm covering this topic and why I'm covering it the way that I am. I did a poll online today to see whether I should do a video on 3D milling surfacing or on my Swiss stuff. It was overwhelmingly people wanted information on 3D surfacing. And this is a super common thing. I think that I struggled with it for a long time, and when I sort of crossed this threshold was quite a while back at this point, but I think it really made the difference between being able to handle every single part that comes across and have it turn out awesome, and sort of struggling or having things turn out good once in a while. And it's really the question of what toolpath should I use here? And this comes up a lot, or why does this toolpath exist, or what is this toolpath used in, or where should I use it? All of those questions. And I first want to say I don't think that the ultimate 3D toolpath exists yet. I also don't think that I'm the only one asking the question of does it exist, or what would it be, or what does it look like? And I can tell you that there's every major CAM system is really, this is what they're chasing right now, is the ultimate 3D toolpath. And it's basically, can you find the toolpath that allows you to, that supersedes all of the other toolpaths and just gets rid of this question. And the reason everybody's chasing it is because this is a huge issue, and it's really difficult to explain to people when they should use a specific toolpath. I mean, I've spent probably 2 or 3 hours just in prep, sitting here thinking about how to best explain this or how to best cover it. So this is I think a really challenging issue. So let's get into it. So what would the ultimate toolpath be? In my mind, the most important thing is that it's efficient. And the reason that I say that's the most important thing is because, let's jump into some CAM and we'll talk while we're gone. Right here I have a parallel toolpath. If I don't care about efficiency, this parallel toolpath, I'm going to tell you right now, it's really inefficient. It's efficient for areas of low slope, areas that don't have a lot of curvature, or areas where the curvature is aligned with the toolpath. But it's really horribly inefficient in areas where that's not the case. As you can see over here, like we're defined to have something like a 20 or 30,000 step over, and it's easily 4, 5, 6, 7 times that step over as it starts dropping off of this high slope area that's perpendicular to the way the toolpath's running. And that's only an issue of efficiency. And the reason is that if I don't care about efficiency, I can just come in here and I can say, well, let's just make that 1,000th, and we'll generate the toolpath. And it's going to take several times, I mean, literally 300 or 3,000 times, I don't know what that works out to be, longer, but now we have our minimum scallop over here. Obviously it is way, way, way tighter everywhere else. So efficiency basically boils down to having a constant scallop, or at least a near enough constant scallop that it's imperceptible and it really tightens up the efficiency there. Let's go ahead and generate this back. And basically all of the sort of primary toolpaths have a focus that's either going to be low slope or areas of high slope. And that's pretty constant. There's a few exceptions of stuff that exist currently, and all of those just happen to have subset problems that sort of violate these last few. But I mean, you can quickly rule out that parallel is not the ultimate toolpath. This is sort of a waterline or contour. It's obviously, it does a better job of keeping constant scallop along the areas of high slope, but in the areas of low slope, it has basically the exact opposite problem, or I mean, the exact same problem, but in an opposite orientation. We wind up with areas with significantly larger scallop through here, and it's not even touching the flat area on the top because it just didn't even generate a pass there. It doesn't have a way to. When you slice this, it just doesn't generate anything there. And so that's important, but I think that the other stuff that I have listed here, which I doubt you can read it, it's on here, but are basically that the toolpath is also attractive, it follows the geometry, and it's smooth. And those three things will basically rule out a bunch of the other options that we have, and I'll go through those two real quick. So it's attractive, it follows geometry. So that's important because obviously these two things, this is a great example right here. If you take and you were to combine these two, you could get something that has a really constant scallop just out of these two. And I can tell you there's a few CAM softwares that are trying to solve this or have solved this basically by combining the two. And it's effectively this right here. What you do is you take on this parallel strategy, you add a slope containment that tells it to stop when it reaches a certain slope. So it's handling areas from 0 degrees slope, like this top surface, down to the 45-degree point. And that's an area where it's not perfect, but it's pretty constant on Scallop, you can see. And then you do the exact opposite onto a contour toolpath. You tell it to only handle the areas or the sections from 45 degrees down to 90. And what you get really is, and we'll see how well this generates here. What you get is really a pretty good toolpath. It just really doesn't do any of this other stuff. It's not attractive in much of any way. There's this big seam, and you'll see that seam through it. The toolpath, at least the parallel, really isn't doing anything to sort of accentuate the curvature. This is sort of a bad example because there's not a whole lot of curvature going on anyway, but especially in areas where you have sort of natural curves. I think I have a good example of that in a minute. In areas where you have natural curves, like this is just, in some places it's going with the curvature, in other places it's going against it, it's sort of random. There's this transition from this toolpath to this toolpath. It's pretty garbage. I mean, this, if you've ever gotten a part from, I won't name names, but any of the like mass prototyping shops, this is pretty well, if they even offer surfacing, this is probably what they're doing. And it's because you can basically template this, throw it onto any part, and you'll get something that's pretty code efficient and pretty scallop efficient. And honestly, if you're going to be bead blasting your part or something along those lines, this is going to do the trick. It's just hacky, and if you really care about machining stuff, or if your intent is to leave tool marks or have tool marks be visible, any of that stuff, I mean, just if you take a small amount of pride in what you do, this is, it's effective, but it's kind of a cheat. All right, so one thing I didn't want to do on this is just show stuff that the toolpaths aren't good at. I think every toolpath that's in here, there are situations where, I don't know, that maybe it's the ultimate toolpath, but where it's probably the right toolpath to use. I came in here, I added some slope on here, but otherwise it's the same. Then I just repurposed these other two operations. So I removed the slope confinement. And if you're just applying this, say, just to a surface like this, or say to like a structural ramp that's in an aerospace part or something like that, that basically it's a surface that has curvature, that has to be 3D machined, or that you're wanting to surface, but that curvature is all in one direction, or it's a constant slope that you can align the toolpath to. Fairly basic stuff like that. Parallel, I mean, you can see this is pretty good. You maybe would want the toolpath actually to run the other direction to accentuate the curvature in the other direction, or to at least have more constant surface speed. All that kind of stuff. But this is pretty good. That's pretty serviceable. And same deal here. This is a tapered area. Maybe you don't want to use a tapered end mill to do it. You just want to surface it. Contour can do pretty good. I just added some check surfaces around here to limit it, and it's constant taper. So, and then it's following the curvature around the part because it's slicing it. That's also perfectly good. Okay, so next, I think I deleted my Scallop toolpath that I had in there, but that's the next one I wanted to take a look at. Let's just toss this out here. Scallop is conflicting because it really depends on how you use it. Let's just generate one and take a look at it. Basically what I got, I told it to stay within the outside boundary, and it did an okay job. This is a little bit different than what I wanted to show. Let's see if I can tweak it. Just tell it contact point boundary. Yeah, so that's more like it. This is more typical of a scallop operation. It did a good job. It's nice and constant step over for the most part, but I can see a few problems right away. So one of them is that as it heads in, it invariably gets to a point where the curve that it's offsetting, so it's based on the boundary. It's offsetting the boundary curve, and that's super important for using Scallop. Basically what it's doing is it's analyzing what the slope is at a given point, figuring out how much it needs to offset that boundary by in order to maintain that constant step over along the surface, and it just continually does that. But at some point, what happens when you offset geometry, and you probably know this, is that eventually the geometry collapses and you get to where you have a radius and then that radius goes away. And with Scallop, that creates a problem. The problem is that this has an equidistant offset, but it doesn't generate an equal scallop, because if you can imagine, the distance from here to here is different than the distance from here to here. Because the distance from your tooltip to tooltip is different from there to there, from here to here compared to here, or from here to here. What you get is basically a cusp that exists. So I think it's actually funny that Scallop is called Scallop, because it's also one of the most renowned toolpaths for leaving scallops on your part. Further, one of the other issues is that it has a tendency, because it's doing these tiny little offsets and it's still a projected toolpath, to get some kind of non-smoothness out here. And that's really sort of a function of, like I said, it's offsetting the boundary. There's some stuff we can do to get around it. But inherently, the sort of default mode for Scallop is you open it up, you sort of select a surface, and you hit generate. And sometimes that works great. Other times you'll get something that's more like this, because that's monolithic. Let's go ahead and select a surface. And this will bring out one of the other issues, is that, like I said, well, I shouldn't say issues. It's an issue and a benefit. It's following the boundary, right? It's generating these passes using the boundary. And so this is a little bit more clean, but now it's not really following or enhancing that curvature. It's enhancing it. It's doing a great job here. It's going the direction we want, but then it's abruptly changing. And so to me, that goes against my smooth characteristic. What we want is, I don't really care if it's going this direction or this direction, but what I don't want it to do is just abruptly change. And you can see I had pointed out before that there was those sharp corners. This pocket collapsed almost immediately, and so on every single one of these corners, you're going to have that same cusp that's going to develop in these corners. It's going to be especially bad right through here. So that's not great, but what I kind of want to show here is that that's manipulatable, right? The fact that it's driven off of the boundary, that it didn't work very well in this situation, because I tried to sort of be lazy and just select a surface, and I wanted it to work, and it's not going to, because of the set of circumstances that I just outlined. What we can do, though, is I made a sketch here. So what I've done is I've offset this sketch, and we're going to instead use that sketch to drive the boundary, and then we're going to limit it using other methods. So let's take a look. What we're going to do is, rather than using that, like I said, we're going to choose this sketch. We're going to get rid of our contact point boundary, and we're going to get rid of this machine areas using boundaries, right? And immediately, let's take a look at what we get. Note we kept the contact only box clicked on. Okay, so we still have the problems where it's collapsing up in here, right? So it's just definitely not going to work to surface an area like this. It's going to collapse. There are some things we could do. Basically, the larger that this boundary is, the further it can go before it collapses, if that makes sense. Actually, the best way to show that is just here. Let's change it real quick. So we'll just get rid of all of this, and we'll say, let's use a circle. And I'm not going to bother to do this perfect. It's not going to be 1000% awesome, but now let's generate it with that. Now the cool thing about a circle is that a circle doesn't collapse as it heads in, right? Now it's not perfectly accentuating the surface, because a circle also isn't going to match up to here, but now you get a lot less of that collapse in the center. And really, if this was perfectly centered, it would do an even better job. But the place where let's go back and undo that real quick. Okay. The place where this becomes really useful is that then say we want to machine this fillet, and say rather than HSMWorks I'm using Fusion and there's no flow, right? This is in a world without flow. Oops, I don't know why I just cleared that. I was talking and not thinking. So then we'll just go in here, we'll blow out a bunch of these surfaces using check surfaces. And that. And we have that set to keep away from those check surfaces. But so now what we're going to get, I hope, is a nearly perfect, yes, success. What we get then is a nearly perfect offset that's nice and smooth, that's following the geometry more or less. I mean, there's some places where it's devolving, and actually I bet we can get this to do an even better job if I include that. Yes, look at that. Okay, so now it's following that. It's leaving a nice, perfectly even step over. It's nice and clean. It's nice and smooth. It's not collapsing anywhere. So I think we're starting to approach. I mean, that's one example of a pretty flexible Ultimate 3D toolpath, right? We had to do some cheating to drive it in a different way, and it might be difficult to get that to work in some instances. But we were able to pull chains off of the model, force it to sort of follow some flexible 3D boundary or some flexible boundary and morph between that and get clean geometry, right? I think that's a win. All right, so I've moved over to this sort of lofty surface. It was built sort of to accentuate the slope. I probably could have gotten some more slope out of here, but I think that this will show some more like real world example of a single surface that wants to change from slope and back, and it is kind of flowy. This is a loft built with two splines that are just sort of organic looking. I tossed in some of the similar stuff in here. Here's that same original parallel. Obviously same deal, great and low slope, terrible and high slope. Here's a similar contour, which actually looks pretty good. Like I said, this doesn't have that low slope on it, but you can still see, I mean, that's probably 3 times as wide. The step over is probably 3 times as wide through there as through this sort of high slope area. So it's not perfect. I tossed in a Radial toolpath just to show that it has its own set of problems. It takes everything that's bad about parallel and sort of adds on another giant issue, which is that so Radial takes you give it a point or a center, and then it's going to take so you give it a point and an angle spacing, and it's going to basically shoot a line out at every angle spacing that you give it. The problem is no matter what you do, it's going to be really, really tight in the center, and then as it gets further away, it starts to have a lot of spacing. It's a problem if you actually need it to run towards the center. Obviously, there's a huge difference between the spacing here and the spacing here. But if you can imagine a surface that's really similar to this, but that this whole center section, or really even if I move this off and over here, and we sort of hide that. You'll start to see that it equalizes it out and it looks a little bit better. Now the difference between here and there isn't so bad, and if this was closer, this starts to become something that's serviceable, but the problem is it has the same issues. Like I said, I made it a little bit better by moving it into the center, but the toolpath has to be aligned with the slope or with the curvature in order for it to be equal. And you get into somewhere like this where it's not, and you have a high slope situation and it's a projected toolpath, and it just can't deal with that. So you can see like this section right here compared to a section in here is probably 10 times the step over. That's just no good. Let's generate the spiral. So spiral works similarly to Radial in that it starts from a center. In this case, they're literally being driven off of the same center, and it generates a spiral that works its way out at some given step over until it hits the boundary. It doesn't have that same angular error as it gets larger, but it still definitely has the problems with high slope. Okay, so stuff that's just generally fit pretty well for this. Place where you would use spiral. If you can imagine kind of a dished surface, or pretty much anything that's low slope but should be turned, like if you're facing, trying to emulate a facing toolpath on a part that you're milling that should be turned, spiral can do a very, very, very convincing job of looking like a turned part. If you start from the center of a round part, spiral your way out, and use a pretty small step over, you can get stuff that really looks like it was turned. And really for round stuff that has a kind of a constant slope from the inside out, dished surfaces or domed surfaces, spiral will work pretty good as long as the slope doesn't get past 40 degrees or so, similar to parallel. Okay, so stuff that would work well. In this case, okay, so this is a morphing toolpath. I didn't spend enough time. I should have generated an offset curve to drive this from. I'm not going to bother to though. Morphing definitely does a good job of nailing the attractive, the follows geometry, and the smooth. In general, it's just inherently, especially on something that's a flowy, curvy thing like this, it's not going to break down too much on sort of real fillets or real geometry like that. It has a tendency to break down. We're actually starting to get a little bit of a collapse in here. You can tell that's why it's tighter in through this section. But it kind of usually tends to fail the efficient test. And it's just because if you're morphing from here to here, this is a huge area, and it's really the surface difference, and so this isn't that big, but the different distance between here and there is quite large, and so with an equal number of steps, and it has to maintain an equal number of steps, even if you're driving it with a step over size, it just winds up with a big difference. It works in places again where there's not much difference. If the delta from the largest portion of the surface to the smallest portion of the surface is small, then you can get away with it, and it will have a gradual change. But it's far from ideal. Here's a simple scallop that's being driven just by this surface. Again, you see the same problems being driven by the boundary. It starts to collapse real bad through here. You'd have huge cusps in through that area, just generally all around here. It's doing a decent job of following. Same deal. You can see those sort of pretty standard collapse of using the boundary directly, and the smoothing effects that happen with that. Again, collapsing over here. Here is a much improved version of the same toolpath. I duplicated it. I think I drove it with a sketch. Yeah, I basically pulled this inside curve and extended it out a whole ton, and then basically the same thing that I did on the other one. I drove it using that sketch on the outside, this curve on the inside, a check surface to keep it from touching the top, and I think that's it. And what you wind up with doing that is just an excellent toolpath. There's some collapse going on here. I could offset that outside boundary a little bit more, or smooth it out some more, and get something that's even better. But like I said, following geometry perfectly, because I use the check surface on the top, I'm just inherently getting a nice perfect sort of stop where this is reaching the tangent point and not going on, within 4/10 or so. So that's pretty good. It's overall very smooth, overall very flowy. It follows the contour. It's equidistant step. There's no parts where this is collapsing, except for some places where it's off of the model. So that's an excellent option. I think if in Fusion right now at this point, this is the go-to toolpath, and I don't know. Here's the part where I don't know if anybody knows how to do this. So I don't want to. I should patent this process, is what I'm saying. I don't want to sound like too much of an arrogant jackass, but this is truthfully, if you're using Fusion and you don't have flow, this is the best or the closest to an ultimate 3D toolpath that you're going to get, at least at this moment. Okay, but we're not right now. I'm using HSMWorks, and honestly, this gives flow a run for its money in a whole lot of circumstances. But let's pop over to the flow. This is flow in HSMWorks using beta mode, so it's not being driven by step over. It's being driven by it's not being driven by number of steps. It's being driven by a minimum step over. And so why isn't flow the ultimate toolpath? I think it's really close. And there's just one inherent problem that means, and that one problem doesn't affect it 100% of the time. In fact, it really only affects it a pretty small percentage of time. But the big issue is that in that small percentage of time, when it affects it hugely, and there's nothing you can do about it. And let's real quick go into the why, and this basically is the quick rundown of why it's being superseded and not why you don't have it in Fusion, or why I'm guessing you don't have it in Fusion. Nobody's ever explicitly told me this, but basically flow is driven off of the UV vectors of the surface. I might have gone into this in another video, but if you can imagine the surface is being built, it's being driven with this loft, with this curve and this curve, and they're being morphed together and over some distance. And what that does is it generates at any given point, there's sort of a rail that runs this direction and a rail that runs this direction. And one direction's the U vector and the other direction's the V vector. And it's being driven off of those. And so what flow does is it pulls those rails out and it uses them, offsets them in the right direction to find the contact point and all that stuff. But it's using those to generate the toolpath itself. So where the problems come up is when you have two surfaces that span together or that link together, but they were maybe built using different methods, or maybe one of them is a generated fillet and one of them was a loft or a sweep. In any case, what they wind up with is the UV vectors or the UV lines on them aren't aligned, and or even on a single surface, if they're just not going the direction that you want because the surface was made in some funky way and it's not really that representative of the curvature, which is sort of an odder use case. The other one's way more common, but anyway, in any of those problems, if the long and the short of it is, if the UV vectors aren't doing what you want the toolpath to, you can't use flow. It's not going to do what you want. It's going to fail on you, and you have basically no control over it. There's some stuff you can do. SolidWorks kind of lacks the tools to do this, but you can pull the surface out, use a different software to sort of realign and correct the UV, the spacing of it and the direction and all that stuff, and then bring it back in. Really, if you're dealing with anybody that cares about their surfaces, once you do that, you've kind of destroyed the integrity of the surface, and you're no longer really working with the same surface, and the likelihood that it looks the same under evaluation or the reflections are right and all of that stuff is pretty small. So I'd really refrain from doing that. But anyway, that's the issue. In most cases, when flow works, it creates basically the ultimate toolpath. I mean, this is a nearly perfect toolpath, and there's basically no denying it. It's almost perfect step over. It's transitioning perfectly from the inside curve to the outside curve. It's perfectly smooth. I mean, just silky smooth. I didn't get into any of this on any of the other stuff, but it has a tendency to have very nice tool point distribution. The breaking points of the toolpath itself have a tendency to be, that's very great distribution, which is something you won't necessarily see on, say, a Scallop. You can see how much grouping there is, or your contour, maybe. Yeah, that one's actually not that bad. But just flow, hands down. I mean, that's almost perfectly uniform distribution of points. It's really pretty hard to beat that. I'm gonna go ahead and shut that off. But I mean, flow has a lot going for it in that department. When it works, and it works well. It also has some underlying benefits in that it's generated based on the surface or based on the UV vectors of the surface. Helps when you have things like undercuts and you're trying to use a lollipop cutter or 5-axis tilting in order to reach someplace that's obscured from a view. If you want more on that, I did a webinar for Autodesk that covered or went into a lot of detail on that. Okay, and lastly, I feel a little bit conflicted even covering this, but it just happened to pop into the latest HSMWorks beta. This is the first time that it's available. It's totally unfair to do any critiquing or any judging of this toolpath based on what you see here. It's, like I said, in beta, very early. Take this with a grain of salt. But what I'm going to say is it's very promising, what I've seen so far. And that is the addition of blend. And we'll take a look at the toolpath that's being generated. But I don't think that's actually that important. If you look at it, you can kind of start to see there are some differences in spacing here, and due to the way that it's generating the toolpath, I haven't quite figured out exactly what it's doing here, but it's not perfectly equal. You can see this is a pretty constant slope. There's not a whole lot of change going on there. And so if the scallop were going to be equal, these passes should be equally spaced. And you can definitely see it's really, there's a tight group here. It's pretty loose up here, and it's kind of loose again down here. So it's not quite perfect in that regard yet. But what's the most interesting thing about it is that it behaves much like flow, but when you're in here, then let's just pop into it. What you're selecting is you're selecting a drive surface, and then you're able to directly select drive contours. Now, so far, the only success that I've had are with drive contours that are the bounding edge of the surface, which you sort of saw what happens when that's the case with Scallop. And I think that if that continues to be the case for Blend, that I think it will wind up with similar issues. But I don't think that that will be the case. I think this is just, like I said, very early in implementation. It can be made much more powerful if I could drive this with my own curves. I genuinely hope and believe that that's where it's headed. I think I'm just massively jumping the gun here by even including this. So anyway, the point is, if this works out the way that I'm hoping, it should basically turn into flow, but with the ability to correct for those issues. Like you can imagine, if I were able to, here, let's take a look. So we can do a split face. What is that called? Face curves. Face curves. So if I were able to pull out some face curves here, and here, let's see, maybe this works. Maybe I can pull these out and drive a blend. No, it didn't work. But you can imagine that if I were able to pull out those face curves and use those as my drive curves for Blend, then all of the functionality within Flow would then exist within Blend, because that's effectively all we're doing, is we're taking, we're just evenly spacing out based on these face curves, our toolpath. So based on that, you get something that's really, really, really similar to Flow, but that if we wanted to, we could use the UV curves if those happen to be the curves that we want. But alternately, we could do something similar to what we did in Scallop and drive it with a totally different set of curves. And that's really where the powerful stuff starts to happen, and we get something approaching the ultimate toolpath. I think I'm going to call it good there. I got some videos to splice together here. If anybody has any questions, or if I missed something, or any of that stuff, just hit me up. Take it easy.